Welcome back to Mustang Physics. Today's topic is electromagnets, super useful in lots of modern electronics and in manufacturing. So the basics is if we run current through a wire, it's going to make a magnetic field. We could drive that current with a battery, or we could drive that current with a power supply like this one. Really anything that'll give you voltage so that you can drive some current, you can make an electromagnet. So I have one here, and that's the purpose of today's video, just to show you kind of what's going on here. So we've got a black iron surround, and we'll see battery, and you can see it's connected to a couple of wires. This one's disconnected right now from the battery, so no current can flow. It kind of operates as the switch, so I can turn it on or I can turn it off. And then really tough to see here. We'll see if we can zoom in enough. But right there, you can see a couple of holes, and nested inside of here is some copper wire. And that copper wire is what's carrying the current. So this doesn't really have much permanent magnetism. If I take a paper clip, doesn't really stick to it. I do have another disc of iron that is the same size. And again, these don't really exhibit much magnetism when you put them next to each other. So if we think back to last time's notes, what that means is that the chunks of iron atoms that are lined up to each other, these domains, within the domains they're lined up, so you have lots of little kind of 1 and 2 millimeter large magnets, but they're not lined up to each other like this. And so these chunks of iron don't have a magnetic field around them because of all the little magnetic fields cancel out. So what we're going to do is we're going to run current through a wire. If we had wrapped it around a nail, we'd make kind of a bar magnet. This is going to make a differently shaped magnet, but a magnet nonetheless. So once we attach the wire, now this battery is driving current through the wire looped inside of here that you saw earlier, and this is really difficult to take apart. And if I release it, now, not so much. Now, interestingly enough, there's a little bit of leftover magnetism once we disconnect it. So if I connect it, you can see very strongly attracted. If I disconnect it, they actually stay together for a moment. And this is something that you saw with the paper clips. If you watched our last video about permanent magnets, what's happened is the iron in these two chunks has become more like this because of the fact that they were in a magnetic field. It lined up those domains of atoms so that their magnetic fields added up to a larger magnetic field. But as soon as we break them apart, vibrate them a little bit, that effect goes away because the magnetic field that they were around wasn't strong enough. What this means is we now have an electromagnet. So we can turn the magnetic field on and off by connecting or disconnecting the battery. We can also manipulate the direction of the magnetic field. Let me show you another demo here. So this demo has 3 compasses, and it's got a little wire. So I'm going to move this up just a little bit so you can see a little bit better. There we go. And this wire, when we turn it sideways, you'll see that there's actually a wire that runs vertically. This wire that's on top and this wire that's on the bottom really aren't involved. It's this wire that runs vertically that interacts with these 3 compasses. And these 3 compasses are just magnets that are free to turn. That's all a compass really is. So I'm going to plug them into my power supply here. There we go. So you can see I can vary the amount of current that I apply. So off camera, when you kind of see my hand go by, that's all I'm doing is turning up or down the amount of voltage applied here. Now, you can see that the compasses aren't all pointing the same way, and that's kind of interesting. That's actually because the compasses affect each other. You can see if I start turning one of them, I'm trying to get them all to sit still, but that's tough to do because if I turn one of them, it actually affects the others. So having lots of compasses in close proximity actually throws the compasses off because they start lining up to each other. Now, north is basically kind of that way where I'm sitting right now. And so the only one that's kind of off is this one, and that's because it's pointing over towards the south of this magnet. But watch what happens, sorry about the noise here, when I turn on the power supply and turn up the current a little bit. You can see that the compasses now turn. So current is flowing in this wire, and that's causing the compasses to turn in a coil around that wire Any straight current carrying wire creates a magnetic field that's curled around it. Now, if I turn the power supply off, you can see the magnets pop back to their original position. At least they would if we let them sit for long enough. Importantly, we can vary the direction of that magnetic field. You can see off to the side here that I'm just reversing the leads. So now current in this wire would flow the other direction, and if we turn up the power supply to drive some current, you can see that now the magnets are coiling in the other direction. Their norths are coiling around clockwise as we're viewing it, instead of counterclockwise like the first time. This ability to vary not only whether there's a magnetic field, but also the strength of it and the direction of it gives rise to a lot of really interesting modern electronics like motors and speakers, which is part of our next video. I hope you enjoyed this video about electromagnets. See you next time.